So, today we are going to continue our discussions on the use of cross product. The topic for today's discussion is torque, and also we will spend some time on angular momentum and conservation laws. So, essentially today we will be focusing on torque and its role in the study of rotational motion of particles. Yesterday we introduced the cross product between two vectors A and B, and we showed that this vector is perpendicular to both the vectors A and B, in the sense that this vector is perpendicular to the plane constituted by vector A and vector B. Then we introduced the notions of angular velocity, or the magnitude of that is rotational speed, then angular acceleration. We also introduced other concepts like radial acceleration and transverse acceleration. And before we proceed on to today's topic, let me spend a few minutes on an important problem which we discussed yesterday. Let me again restate it. We have here a rigid body, this is the axis, x axis here, y axis here and z axis here, and then these are the standard equations which we derived yesterday. The expression for the linear velocity in terms of, it is written as a cross product between angular velocity and the position vector, etc., and transverse acceleration is alpha vector crossed with r. What is alpha vector? It is the angular acceleration vector, it is d omega by dt, and then radial acceleration is omega cross r. These expressions were we did not give you very rigorous definitions, rigorous derivations of this, but we wrote by some kind of analogy. And now these are the equations for rigid dynamics. However, you would have studied earlier the motion of a particle in 1 dimensions and 2 dimensions. Suppose I consider the motion of a particle in 2 dimensions, the particle can go anywhere along, therefore this distance r can change, what you call it as radial distance, and this is what you call it as theta vector, it is already there given. This is the direction of theta once you rotate from here to here. So there are 3 directions, essentially 2 directions in 2 dimensional plane, the radial direction and theta direction or the transverse direction. You also have an axis which is coming out of the board, that is the z direction. So just like x, y, z form a triad, just like in the Cartesian plane x, y, z form a triad, you have r, theta, z forming a triad here. Okay. Now we derived those equations here. The velocity vector is r dot times, you start from this position vector and differentiate it with respect to time, and differentiating with respect to time you get this quantity. Now this you realize the coefficient of unit vector er is the radial velocity, whereas the coefficient of e theta is the angular velocity, and anyway it is only the magnitude, this whole thing is angular velocity, this is the rotational speed, that is the terminology. Now since the particle can go anywhere in this 2 dimensional plane, if I fix r, if I say that the particle has to only rotate along a circle, that is what happens in the case of a rigid dynamics. Even though the body is rotating about an axis, I consider a position here, then this is the radial direction, this particular point is going to sweep a circle, that circle is what going to correspond to the circular motion of the particle here. Once I fix r, r dot is 0, d by dt of the radial coefficient is 0, then automatically you will get here the radial velocity is 0. For a rigid motion, you consider a particle which is fixed, radial velocity is 0, but whereas the angular velocity is not 0, fine. Now what is omega? Omega is this is the omega vector. How do you define this omega vector? Omega vector is defined as its magnitude times the unit vector. This is the sense of rotation is described like this. Now I can calculate what is omega cross r. Omega cross r is omega times Ez times the vector r is r times unit vector along radial direction. Now this is omega times r times what is Ez cross Er? Ez cross Er would be E theta, something like I cross j, unit vectors I cross j is k, j cross k is I, in that sense I will get here E theta. Now you see here the whatever equations we have here, whatever results you get from here, they are obtainable from the free motion of a particle in 2 dimensions subject to the condition you are fixing the radial coordinate. Okay. So therefore it sorts of what we are doing here, it is a sort of vindicates our derivations here, these equations. Then you take, I want to calculate the acceleration vector is dv by dt, dv by dt is d by dt of, I will write down the full expression here, I am not going to fix the position of the particle right now, I will derive the full thing and see what I am going to get. So r dot er plus r theta dot e theta, differentiate this and I will get here, once I fix the position of a particle then I will get here. Therefore it is a surprise that the acceleration will have the radial component as well as tangential component, whereas velocity have only tangential component and no radial component for a rigid motion. Now I should be able to get it from here. Yes, I have this expression for at which we yesterday derived it, and alpha cross r is, what is alpha? Alpha vector is the angular acceleration, therefore theta double dot times Ez times r times Er, this gives you r theta dot times Ez. This is same as, this expression is same as here. Now the radial acceleration looks somewhat complicated, actually not, omega cross r, omega vector is this quantity and omega cross r vector we already calculated here, so that I can put it here, then I will get here r theta dot square times Er, which is same as I think Ez E theta, Ez E theta, I am doing it in the other way, therefore I should have one minus sign here, therefore this expression is same as what I have over here. This sort of tells you that even though rigid dynamics is a special subject, you can always study this in a sense if one axis is fixed from the motion of a particle in 2 dimensions. And so with this I will proceed further for today's topic. Today's topic for discussion is torque and angular momentum. Okay. Now what is the motivation for it? Now how do, when to displace a particle, I have a particle here, I want it to move, only way I can do it by a force should act on it. So it is the force which is responsible for the translational motion of a body. If the body is here, if I apply a force, it goes to some other position, from here to here this body has been translated. So force is the one which is responsible for the translational motion. Now the question is, it also produces an acceleration on the body. Now we consider the following situation. Suppose I have a door, I have a door like this, these are all hinges, there is one in the one here, there is one here, and okay. Now when I want to rotate this door, when I want to rotate this door, if I apply the force here in whatever angle, the door is not going to rotate. If I apply the force here normal to it, the door will rotate, but our practical wisdom tells us from our day to day life, if I apply the force here normal direction very close to this edge, then the rotation is very elegant and easy to produce. Okay. Now this is what is called as moment of a force. This concept, there is a force acting on a body and then there is a rotational effect happening. This concept, this effect is described by what is called the moment of a force. Moment of a force, or it is also known as torque. It has got several equivalent names, moment of a force, or also a couple. We will see what it is. And so just like if I have a force, it can produce acceleration on a body. It is the force that is responsible for causing acceleration of a body. I have here a torque can cause angular acceleration. So when the force acts at this particular one normal, let us say that this door is on the plane of this board, then a normal force acts on it, then the door will rotate, and when the door rotates, it is going to sweep an angle with respect to the frame of this board. So what is the rate at which that angle will change? What is the rate of change of that angle? That introduces the angular acceleration. And now we will derive an expression for moment of a force, we will properly define it. Okay. Moment of a force on a single particle. Okay. So let me fix the axis like this. This is x axis, this is y axis. So I have the particle here, this I will call it as r vector, and this is r vector, this is the particle here. Then there is a force acts like, there is a force acting like this. This is f vector. I can produce this. I will also now the torque, it is denoted by tau, torque tau. It is described as, it is defined as the cross product of the position vector and the force acting on it. And so one thing straight away clear is this torque, the direction of a torque is both, it is perpendicular to the position vector as well as the force vector, and right, and it is given by right hand, it is given by right hand screw. This you must keep in mind for the direction, right hand screw, which we described in yesterday's class. Now therefore by definition this is nothing but r times f times sin theta, or r times what is f sin theta? This is, this whole magnitude is f. So if I drop a perpendicular from here, this is if I drop a perpendicular from here, this is the theta. I will take this as sorry, this is theta, not this. So this is going to be the f sin theta is what you call a f perpendicular, f sin theta. This is cos, this is sin. So this is written as r times f perpendicular. This is what f perpendicular. You know this I can also write it in a different way. How? I drop a perpendicular from here, this is theta. So, when I drop a perpendicular from here, this I can write it as f into r sin theta. R sin this triangle, right angle triangle, I can take this is r, therefore, this is r sin theta. I can view it in both ways. So, this is written as f into r perpendicular, this quantity is known as r perpendicular, right. Now, what about the dimensions of torque? Force, we know the dimensions, and r is the distance, therefore, force into distance, this has the dimensions of energy or work. Work done, right. Now, whereas the work done is a scalar quantity. If a particle moves by a distance, if a dx, let us say if a particle moves by distance dx, the force acting on it is F, then the work done in moving this is F dot dx, infinitesimal work, right. However, it has the dimensions of energy, but torque also has dimensions of energy, but it is a vector quantity. So, you need to keep in mind. We had seen similar pair, one scalar and another vector, which have both the same dimensions, we had seen in couple of classes earlier. For example, the angular velocity omega, it has got dimensions of it is what, d theta by dt, d theta is in radians, therefore, it is time inverse. What about frequency, angular frequency I mean, angular frequency is what, how much angle it sweeps in whatever the time duration. So, this also has T inverse, whereas one is a vector quantity, this is a scalar quantity. So, such pairs do occur in physics. Okay. Now, I will give you a simple illustration, suppose I have a screw like this, I want to rotate it. What do? I want to rotate it. So, we have a spanner like this, I will take a different colored chalk just to indicate the spanner. This is how a spanner will look like, right. Now, if I want to rotate it, I will apply a force here. If I want to rotate this, I do like this, this is our day to day experience. On the other hand, this is the force. Now, if I apply the same force here, it is not that easy to make the screw rotate, advance forward. So, longer the distance, it is better. So, if I want to do it in a very elegant way, easy way, what I need to do is I need to slide a pipe of considerable length, then I apply it. If I do it, even less force is sufficient because it is r cross f. Since I am increasing r, tau is going to be equal to r cross f. If I have a long arm, even less force is sufficient enough, right. So, if you when is tau 0, when is the rotational effect 0? In order that to happen, if if the force is 0, if there is no force, then certainly you cannot rotate, there is no torque at all. On the other hand, if r is equal to 0, that is the line of action of force passes through the origin, the line of action of the force passes through the origin, this is the, here this is the line of action, if the line of action is also along this, then there is no way it is, right. Other one is the angle between these two, that is what is 0 or 180 degrees, is it right. So r cross, we need to keep in mind that this is a vector product, therefore we need to keep in mind the various properties of r cross f, they do hold, we had seen it, what are the various things, right. If r reverses the sign, f reverses the sign, then the tau will remain the same. We will do a simple illustration. You need to keep in mind this r cross f, when you take the product, what is the direction of tau? The direction of tau is as specified by the right hand rule which we had seen yesterday, r cross f. So one is r, this, if this is going to denote r, middle finger is coming out of the board, f is actually from here to this side perpendicular to this, then the thumb will tell when r to f, when you rotate, the thumb will tell it will advance in the forward direction. We will do a simple illustration, this an example. So I have a point A here, and then this is the particle P here, this is the axis coming out. I will set up the axis as this is x axis, y axis. So it is simply the particle is falling mj, it is a particle which is falling, the mass is m, gravitational fall, right. So I will take a point here, this is mj. I want to calculate what is the torque on this particular particle with respect to A due to the gravitational force. Now this is a quadrant, so here I will have it this as point as x, this is y axis below, therefore minus y I will say a typical point. So this is r vector, this is theta, that is now what is tau? Tau is equal to whatever it is, radius of the magnitude of this times the force times sine of theta, this is same as this. Remember we always take the small angle whenever we take the cross product, this is the theta. Now you may ask me, sir, why don't we make use of this definition of the cross product, right. We will do it, and when we do that, what will happen? Tau is equal to r cross f. Remember yesterday we wrote down this definition, I, j and k, this coordinate is x, this coordinate is minus y, this is 0, and mg has only the y component, therefore 0, it is a positive force when it moves towards it, towards the ground, towards the center of the earth. So this when you calculate, you will have I into this is 0, j into this is also 0, and only surviving thing is k into x into mj. So this is nothing but mg x into k. What is sin theta, sir? This is theta here, sin theta is what is, this is opposite, this is adjacent, therefore this is x by r, right. Fine. Now this is x, sorry, this is x, so this is opposite x by this radius, this what will give you sin theta, therefore this is same as this is sin theta is x by r into mg into sin theta. So, the x by r, what is happening? I am making some mistake. I will correct it. It's not a big deal. R into mg into sin theta is x by r. R and R will cancel. So, I will have x mg. Here I am writing only the magnitude. If I do like this, then direction I have to fix, again right hand thumb rule. If I write these vectors properly, then automatically the direction will emerge out, that is the moral. Okay, you can do it either ways. The next concept is angular momentum of a particle. Now we are talking about the moment of a force. Similarly, we can talk about the moment due to the angular momentum. So, let us consider a particle of mass m and its position, it is with respect to a coordinate system, it is at a particular position vector r and its momentum is p. Then its orbital angular momentum, the torque or moment of a force is, now let us compare this with linear dynamics. Torque or moment of a force is the rotational analog of force, it is generally said, rotational analog of force. What do we mean by this? Just like force is what that is responsible for a body to move, have translational motion, it is torque that is responsible for an object to rotate about an axis or a door to swing, etc., etc. Now what about angular momentum? The angular momentum is the rotational analog of S. So, the angular momentum is the rotational analog of S, linear momentum, yes. Now you might notice that we are gradually equipping ourselves with various concepts and their mathematical definitions, so that we can handle problems involving systems of particles and rotational dynamics. Now you may ask me, sir, today we have got two quantities, tau, this is defined like this, L which is defined like this, which of course even in linear motion we have it to be like this, we have defined it earlier. Is there any connection between these two? That is what we are going to next topic for discussion. It is fairly simple, relation between it is fairly simple. So we start with L is equal to R cross P, this is the definition of orbital angular momentum. So let us differentiate with respect to time. How is it justified, sir? In general, neither the position of particle is going to be constant, it will vary, or the momentum of the particle also is subjected to change. Therefore, there is meaning in talking about d by dt of L. This is d by dt of R cross P, this is equal to dr by dt, it is a distributive, derivative is what you do is keep this constant and differentiate this, plus keep this constant, differentiate this, that is what we are going to do, plus r times dp by dt. dr by dt is going to give you velocity vector, therefore dr by dt will give you velocity vector, velocity crossed with momentum vector is what? Momentum is m times v, therefore that will vanish. So you are simply left with, what is dp by dt? Rate of change of momentum known as by Newton's law force, good. Right. Therefore the what is r cross f? R cross f is the tau, torque acting on the body due to this force. Therefore we have a very elegant relation, dl by dt is equal to tau. You say that the time rate of change of angular momentum, the time rate of change of angular momentum is equal to torque, and okay. This is something similar to when you compare this equation with what you call the kinematics in 1 and 2 dimension, general Newton's equation. What is that you get? This is something, compare this with dp by dt is equal to f. Now this is not enough for us, the tau acting on one single particle is not sufficient, because we are studying system of particles and in general a big rigid body, therefore, and what about the orbital angular momentum, etc., other quantities we have introduced for a system of particles. It is again fairly simple, because L is a vector quantity. So vectors are you can add it if L1, L2, etc., or the angular moment of a system of particles, n particles, then its total angular momentum is given by this. So what is Li? Li is the position vector of ith particle crossed with the momentum vector of that particular particle. So just for clarity I will write, you can think mi times vi. So the total angular momentum is, I can write this way, I have already written it, is I running from 1 to n, this you can also write it like this, Ri cross Pi, I running from 1 to n. This is the definition of angular momentum of a system of particles. How is it justified? L is a vector quantity and vectors you can add, just like on a particular particle force F1 acts, F2 acts, F3 acts, you can add all of them. And now we will talk about what is the dl by dt of this quantity. dl by dt is d by dt of summation over I 1 to n Li is equal to, I can differentiate each of the terms and then add, what is dli by dt? Tau I, it is a vector, sum over all vectors. Therefore the sum of the rate of change of total angular momentum is what is equal to sum of all the torques. This you can call it as capital T, capital tau rather. It is the total torque that is acting on the system of particles. It is the total torque that is acting on the system of particles under the. Now we will I consider tau I consider tau I. What is tau I, sir? The this is the position vector of ith particle times Fi, right. So, this is equal to Ri times, we had already seen the forces are, there are two kinds of forces, one external forces like gravitation, if you put a charged particle in an electric field or a magnetic field etc., and they can be internal forces like tensions, compressions, interbody attractions etc. And so, I will say that Fi external plus the internal forces corresponding to the ith particle. See, generally if you look at it, the internal forces are of something like action reaction type. You take in a gas two molecules, whatever force one of the, when two of these molecules they collide, one of them is going to exert a particular force on the other molecule, it will, you will get a reaction on this first one due to the other molecule. Therefore, the internal forces are of action reaction type, and then and these forces do not contribute, they are in opposite directions, and then they do not contribute. So, we can say that tau internal, the tau internal is extended due to tau external only. Therefore, I can write now dl by dt is equal to, so this is so this tau has reduced to just external because the internal forces are not going to contribute, they are of action reaction type, we can write as tau external. Okay. So, this is something a bell should ring when you see this. This is something similar to we have earlier seen. What is that? The rate of change of total momentum is equal to F external, right. Despite the translational motion, rotational motion are of different nature, you can see the remarkable similarities with respect to the basic governing equations in both the cases, right. So, you say that, now we can say that the time, this is rather important, the time rate of total orbital angular momentum okay. You have a kind of a mnemonic ohm, not very common, the time rate of total orbital angular momentum of a system of particles about a point or about a line or about a line or an axis, about a line is equal to the sum of the you should not say simply torques, external torques, that is important because internal forces are not going to contribute anything. External torques, that is the torques due to that is the torques due to, just complete the sentence, external forces alone. Okay. So, what about now we will talk about conservation of angular momentum, when conservation of angular momentum. Conservation of angular momentum. Okay. If tau external is equal to 0, then implies equal to 0, then dl by dt is equal to 0. This implies what? L is a, L does not change, or L is a constant of motion. L is a constant of motion. L is a constant of motion. You say that in technical language, which you should learn to use, L is conserved. Now, what is the next? What is the natural question you would ask? You would like to compare this situation with linear motion situation, right? So, what is that you have? Dp by dt, when you have dp by dt is what you call it as F, the force acting on it. When F is 0, if F is equal to 0, then yes, the linear momentum is a constant of motion. Or equivalently you say that P is conserved. It is true even in the case of system of particles, because even though I have written small p to denote the momentum of a single particle, this relationship is true even in the case of system of particles. The reason is momentum is a vector quantity you can add. The total momentum, we have done it, the total momentum of the particle just a few minutes earlier is vector p1 plus vector p2 etc., all of them, and right, this is. So, when is orbital angular momentum a constant of motion? When the external torques vanish. Right. Now, we will do a simple problem, we will do an illustration and then now let us consider a particle which is moving with a constant velocity. This is an example, particle moving with a constant velocity. This is one of the, this is a simple system, and let us consider the particle is moving in this direction, let us say that. Okay. At some instant of time the particle has to be somewhere here, right. Now, with respect to at some instant of them the particle is here. So, this is the position vector of the particle, this is the origin of the system, coordinate system. Okay. Then I will I will project this, I will produce this, sorry, this is the particle, this is theta, strictly speaking not necessarily we will see that. I will drop a perpendicular from here. So, this is r, therefore, this is opposite corresponding to sin theta. Alright. So, the description is like this: a particle is moving with a constant velocity is v, therefore, it is v is a constant velocity. Therefore, its momentum is m into v, that is fairly simple. Now, I want to calculate L is equal to R crossed with m into v, R cross p. This is by definition what do we have? R, which is the magnitude of vector r, then m into v into sin theta, and you know what is little r? Little r is this quantity, and little v is magnitude of this vector, is very standard. What is its direction, sir? This is the position vector, this is this is the direction of position vector, and momentum is along this. Therefore, when I take this right hand thumb rule, I will look into the smaller angle, and so this will the direction is what? Is it coming out or into the page? Yes, into the page. The direction of P, I will write here, the direction of P into the page at this particular point, and right. Now, what I will do is, as the particle moves along the straight line, what is Om? I want to calculate. So, what is I want to this is I will call this as let us say sin theta is equal to Om divided by r. This implies Om divided by r. So, I will calculate. Sorry, I have not indicated the direction. This is a vector. This is a vector. If I simply write this is not correct. This is the direction. Okay, fine. So, now I will have L into, this is the magnitude alone I will write, so that I need not worry about this, R into mv into Om by Om is r sin, Om is r sin theta, Om is r sin theta. So, therefore, I have L is equal r sin theta, 1 minute please, Om is r sin theta, yes, this r sin theta, I will write it as r sin theta into mv, this is Om, r sin theta times mv. Now, we are done. The reason is, as the particle moves along the straight line, we have calculated what is the magnitude of angular momentum. Its magnitude of angular momentum is this particular length, that is what Om times mv, right. So, this is sin theta is equal to Om by r, that is what we have done. So, from this you come to the conclusion. What is the conclusion? Whether the particle is here or the particle is here or the particle is here, it does not matter, it is always this Om, it is always this distance Om when you calculate the magnitude of the orbital angular momentum. Theta will vary as it moves along, however, this is always the same, this Om is the same. Therefore, this implies as the if a particle is moving with a constant velocity, then its orbital angular momentum with respect to an origin remains a constant of motion. So, L is a constant of motion. Therefore, what will happen to dl by dt? So, there is no torque. Okay. Here you can see that so with this I think I can let me summarize. Today we started with the definition of a torque and angular momentum, then we showed that what is the connection between torque and angular momentum, then under what conditions L is conserved, under what conditions the torque is, then we had considered a few simple examples of the situation involving cross products, calculating torques, and in this particular problem we realized that L is a constant of motion.